Welcome to a lesson with Dr. Powell. Let's take a look at an optimization problem in calculus. We're trying to minimize something. We want to find the x value the radius of a cylinder that will maximize the volume of this can if we have a particular surface area that we're working with. Suppose that we want the surface area to be 40 square inches. How many inches should the radius be x in order to maximize the volume of this can? Okay, so how would we work with that? We want to maximize volume. So whatever we want to maximize represents the output of the function we want to write down and do calculus on. So we think we're maximizing volume. Let's come up with a formula for volume that depends on x. Well, we know in terms of x, we know what the area of the base of the cylinder is. It's pi times radius squared. Radius is x. So pi times x squared. So pi times x squared, that represents the base. And volume is equal to base times the height. So now we just need to come up with an expression for height in terms of x. Well, what do we know? We know the surface area is 40 square inches. Surface area, what is that? That's the base plus the base, so it's twice the base, 2 pi x squared, plus the lateral surface area right here on the side. How do you get that lateral surface area? Well, if you took the perimeter, the circumference of this, so you have a radius of x, the circumference is 2 pi times that, so 2 pi x. And then if you cut right down, you cut it and stretched it out, then you look at it a little better. So that would be 2 pi x, or you don't stretch it, you unravel it, is maybe a better way of word for saying it. So 2 pi x right there, right there, and then you have your height. Right, so we know of height times 2 pi x. And I'll just use a letter for h because I don't know what it is, so just use a letter for something you don't know. So 2 pi x times h. So 2 pi x h. So we have this relationship. This is actually a relationship between h and x. Okay, so we could solve for h if we wanted to in terms of x. So we'd get 40 is equal to, so I'll just write this again, 2 pi x squared plus 2 pi x h, subtract, okay, and that's a plus, okay, subtract, in fact, we can divide, well, whatever, we can divide both sides by 2, that looks a little simpler, and we can divide the pi over to the other side, because you can divide out of each term, you can factor it out and then divide out by, but anyways, so you divide everything by 2, you get 20, divide everything by 2, then divide everything by pi, or just divide everything by 2 pi, there you go. So 40 divided by 2 pi is the same thing as 20 over pi, and that's going to be equal to x squared plus xh. So if you get 20 over pi minus x squared all over x, because you subtract that over and then divide by x, that'll be equal to h. Okay, so the height, 20 pi minus x squared all over x. Okay, awesome. Now you see this, so this is our formula for volume. And we can think of this volume now as a function expressible in terms of just the variable x. So volume of v of x is equal to that. So notice this x and x squared, you get a cancellation. X, you left with 1 power of x. All right, x squared over x, the same thing as just x here. Of course, assuming x is non-zero, but we're going to be assuming that. All right, so that's our volume. Pi x times that, and okay. And then we can multiply that out. If we multiply this out, we end up getting, so the pi cancels in the first term as it comes, pi over pi, and then we get 20x. So we have 20x, and then as this distributes to that part right there, we're going to get minus pi x cubed. So pi x times x squared. So minus pi x cubed, and that's just, we're just simplifying the form of the volume still. So that's still the function. Now we're going to take a derivative of this, all right? And the derivative is simply 20 minus 3 pi x squared. Okay, so it looks like if we set that equal to 0, we're going to get, can move this to the other side, divide by 3 pi. So we're going to end up getting x squared is equal to 20 over 3 pi. So x is equal to plus or minus square root of 20 over 3 pi. But really, we want x to be positive, so we're just going to look at that. So x is equal to 20 over the square root of, so the square root of quantity 20 over 3 pi. And does this represent a maximum as desired? Let's just look at the second derivative real quick. Second derivative is pretty simple in this case. And if you do that, you're going to end up getting negative 6 pi x. And since this is a positive number coming in, that's going to give us a negative second derivative. So it's going to be concave down at that critical point where what makes the first derivative equal to 0. Concave down at such a point is a maximum. So we have verified that indeed, by a second derivative test, that this does yield a maximum volume, and we can, and that's our radius right there. Thanks for watching.